This is day 70 of daily LeetCode. We are back once again. Yesterday we were working on a problem called Flatten 2D vector. This problem mostly was a waste of time. I got a tip from the copy ninja himself, who mentioned that we should have taken a look at the like and dislike ratio. Signifying this problem was probably something that we probably should have ignored, but I was just clicking random problems to do, which I didn't even realize, and I said that we would focus on review. So this problem, ultimately in the end, I was just reading the solution. They went for pretty much a two-pointer approach with basically row and column. They call it inner and outer. I called it R and C. So basically the same thing we're looking for. We got lost in the sauce by implementing all these methods, and even index is invalid, which is technically just the duplicate function of increment. So it just got all a little messy, but ultimately I think we intuited the goal solution, but then we just got a little confused. And then we had a comment as well. Control Copy Ninja said, this problem cooked you. I'm not gonna lie, this is actually true. And I got lost in the pointer sauce. So this problem, right, we should have, if we're gonna do a random problem, we should have done one from the grind 75 or the NC 150 or the grind 150. But yeah, so we should have did something like that. That being the case, I didn't get to do any system design reading yet, so we have to do that. And also we need some more reading for the ADM. But we have 30 minutes today, and the goal would be to do just review problems. And yeah, so I think after today, tomorrow on, let me see, Tuesday. On Thursday, we should return to the regular 2-hour schedule. So there will be many more nuggets to digest wisdom's algorithmic nature. And I also I'm just that guy commented that yesterday was a special day. This is true, particularly because of the number. So that was important. Also, Thomas had the same intuition, so that was important as well. But yeah, also shout out to all the people who joined the Discord recently. It is growing very quickly. So you're going to definitely want to join the Hyperbolic Coding Coalition as soon as possible. So yeah, we have 30 minutes today, so let's just do it. Longest substring without repeating characters. Goal time will be linear time with constant space. Given a string S, find the length of the longest substring without repeating characters. So we have ABC, ABC, BB. Right, if we map this problem statement to the example, we're going to find the length of the longest substring, which means our output is going to be a number. This does make sense. And we want the longest substring, right, such that there's no repeating characters. Answer here being ABC, right? And this problem, we can do the longest substring we can create without repeating characters is of length 1. Right, because this whole string is of repeating lengths. Then we have PWW, KEW, the longest string without repeating characters is WKE. Looks like S's length can be empty, and S consists of letters, digits, symbols, and spaces. So if that's the case, we know to start, right, that if the string is empty, then what we'd like to return is a length of 0. Right? If the string is empty, then there's no substring we can create at all, even considering that it could be the longest. So that's important to consider, right? And maybe we can intuit that problems with strings, usually a good angle to start is based on sliding window patterns. What if we did something like that, right? Whenever we have to minimize or maximize something, it can be computed as a function of some contiguous set of elements, right? Sliding window pattern is usually a useful way to go. So if we look at A, B, C, right, I'll make this even bigger. How do we know when to restart, right? So if we had something like this, we had A, right? Let's say we assume that our window starts at A, then goes to B, then goes to C, right? And on each iteration, right, we'll be able to assume that our window, right, is the longest. At each iteration, we'll assume that our window itself is the longest substring. So basically, the prerequisite to enlarge the window is that there must not be any repeating characters within it. So we start at A, there's no repeating characters. We add B, there's still no repeating characters. We add A, B, and C, there's still no repeating characters. Then as soon as we add A, we know that there's a repeating character. So basically, we need to know, you need a way to know pref in constant time if string, if car, or if window has dupe character. So we need a way, preferably in constant time, to know if window has duplicate characters, right? Because as soon as we add A, right, we know that we have a duplicate character. So things we could do, right, we could have a set, right, maybe a set. So potential solutions for this, we could have a set of cars in the window. Another angle could be, you could have a, what do they call it? A flag map, or a character array, or basically it's an array, right? Usually of the size of our input space, right? English letters, digits, and symbols. So probably a length of 128, right? Right. So they have 128 elements, right? And it's just a Boolean flag map, or I guess it's a map of numbers, right? Or an array, right? Where each indice, right? We can add a dot, 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 128, or this would be the 128th element, right? Where each indice represents an ASCII character. So we can imagine, right? Let's just say that this is 64 or 63, right? The next one would be 65, which would be A, right? So lowercase a would be stored here. I mean, this spot in the array would signify the number of occurrences of A, right? That way we could just subscript our array with the ASCII value of the character, right? And then you'll be able to know how many of this number exists. So, right, so that's another, how many of this character exists. So that's one way we could do it, right? And if we layer that on top of a sliding window, then we should be okay. So if we look at this again with our new found information, we have A, right? So we'll add, right, an occurrence for A in the flag map, in the character array. Then we'll have B. B is right after A. And I'm also not curious, should we consider lowercase letters and should we consider lowercase letters? Should everything be lowercase? It doesn't really say, so maybe we'll just we'll be case insensitive. So capital A and lowercase a will map to the same indice. All right, then we'll add B. B will be 1. Then we'll add C. C will be 1. Right, and then we'll add A, right, which will now be 2. There'll be 2 A's. Right, now if that's the case, right, now we're stuck on this index, right, because our goal, right, we're going to want to shrink our window, because our window would be A, B, C, A. We want to start from our left-hand side of the window, increment forward, right, so we want to shrink our window. We'll start at A, we'll remove one occurrence of A, right. Now I have BCA, right, which is fine, and then B we'll find B, right, which will shrink us to cab. Then we'll find C, which will shrink us to ABC. All the while we originally already found ABC. So I think the way we're going to want to go about this, right, we're going to want 2 pointers, right, left and right, right. And we iterate while right is less than s dot length, right? And for a particular character, right, we'll increment car in car array, increment occurrence in car array, right? Like we said, we'll change A to 1, And after we do that, right, the way we increment the occurrence in the character array is going to be based off of the right pointer, right? So after that, right, now we're going to want to do our check, right? If after this incrementing of the occurrence in the character array is greater than 2, we want to shrink our window until that's no longer the case, right? So in this case, when we start, you know, left has to be, have another while loop while left is less than right, while 0 is not less than 0, right? So we start the same element, there can't be a duplicate, right? Because the window is of size 1, right? But we'll say while left is less than right, and let's just say, we'll call it occur, right? Sub right, occur sub right, right, is greater than 1. All right, if it's greater than 1, right, then what we're going to want to do is do occur, right? We'll say occur sub left minus equal 1, right? And then left plus equal 1, right? So basically we're going to shrink this right-hand side of the window until occur sub right is no longer greater than 1. So if you look at this A, B, C window, right, we increment A here, this fourth character, right, we would have occurrence of 2 in the character array, right, while left is left and right, right, left is 0 and 4, right is equal to 0, 1, 2, 3, index 3, right, and occurrence sub right, which is this A here, they're pointing to the same value, is going to be 2, which is greater than 1. So occur sub left minus equal 1, right, left is equal, right, so not occur sub left, we want occur sub S sub left. Right, because we want to index the occurrence array with the actual ASCII value of the character, so I have to do that car code at, right? Right, so we get A minus equal 1, so we set this equal to 1. We do left plus equal 1. Now our new range is going to be BCA. Right, and then from there, we'll have validated that our window, right, is a window containing no repeating characters. So we'll say, we'll just call, you know, something like let max len, right, equal to negative the infinity. We'll say max len is equal to the math.max of max len, or right minus left. Now let's see how we can calculate the range of our current window. Right, if we have a new range, like we said earlier, right, of A, B, C, A, right, we just took off A to have this new range of B, C, A, right, it would mean that left is at index 1, and R is at 0, 1, 2, 3, index 3, right? What's the range of that? What's the range of that window? Right, we know that the answer should be BCA, right, because that's the length of the window. But how can we derive that from the values L and R? If we do R minus L, we'll get 3 minus 1 equals 2. So we'll do right minus left plus 1 to create that range value. And then we should be able to return max length. It's okay to set this to negative infinity, since we know that when the string is empty, we'll return 0, which means there must be at least one character. If there's at least one character, we should at least get a max length of 1 of a substring without repeating characters. So let's try that. We'll say left is equal to 0. Duplicate this to say right is equal to 0. Right, and we'll delete. Just take this how we were doing it. Right is less than s dot length. Right, and at the end we're also going to want to do right plus equal 1. So we keep going forward. We're going to want our occurrence array, right? And we're going to want to set it up to start, right? To include the range of all English letters, digits, symbols, and spaces. I think we can use 128 spots, right? So 0 to 127, and we'll just say occur dot push 0 to start. Now you want to increment the occurrence of the character array. To do that, we'll say car, right? S sub right will give us the character, right? And to increment that, we can do occur sub car dot car code 0 right plus equal 1. We can say all left is less than right, and occur sub s dot right dot car code at zero then we'll say occur sub s dot left car code at 0 minus equal 1, and we left plus equal 1. So yeah, let's see if that makes sense. For our first case, we have A, B. I guess we'll run it to start and then see if it didn't make any sense. We should double check before, I feel like. So we have an empty character. Right. So I wonder what the character code for space is. It might be outside of the bounds of 128. Okay. The character code is 32. So why are we returning -1? So s dot length 0 is less than 1, right? Car at s would be space. The car code at the ASCII value for that character would be 32. Say plus equal 1. I'm wondering if you can't do plus equal 1. So let's just print occurrence afterwards to see. So you see you can't do plus equal 1. So we do left minus left is less than right, so 0 is not less than 0. Oh, we only do max length in here, and I think that's the problem. This is just to fix the problem we have a boundary, right? We always want to take the max length property, because it's after this that we validate it. When we start with one character in the string, there'll be no duplicates, so do max length. When there's 2 characters, there could be a duplicate, so we fix it, then we can take max length again. So that makes sense. So what's the time complexity? It takes us 128 operations to create the character array. And the sliding window pattern, what operations are we looking at? We're iterating over the entire array. Where the left is less than right, and occurrence sub s sub right. I would say this is linear time, because at worst the entire string, for example, we know that the max length of our string can be 128 characters. So let's just say we have A, B, C, right? 1, 2, 3, dot, dot, dot. Let's just assume the last character is space, even though it's not. Let's just assume the last character is like exclamation point. The worst case scenario is that A is at the end. If A is at the end, right, then a cur sub S sub right, we'd have a duplicate character. Then we'd have to take our left pointer, which started at 0, all the way across the input string to this A here, which would give us a time complexity of 2 of n, which basically would just be linear time. Now I would say our space is constant space just because the character array at max will have 128 indices regardless of the input string size. Oh, coin change, right? So we were hoping to actually, so the last time I did this problem, we had an exponential time algorithm because we could visualize it as a graph. I kind of don't have to read this statement because I've read this, spent a lot of time on this problem, but now I know after reading the ADM, right? We're basically looking for the, basically the problem is asking, right? We have coins, 1, 2, and 5, and amount which is 11, and we want the shortest denomination of coins, right, that can get us to the goal amount. In this case, the shortest denomination is 5, 5, and 1, which is 11. In this case, there are cases where we have no path to the goal amount in which we would like to return -1. And then we have coins, right? When we want to get to 0, we can always get to 0 basically. So one thing we can do is say if amount is equal to 0, we can always get to amount, right? By using, if amount is equal to 0, we can always get to it by using no coins. Right, so I think one way we visualized this problem before is a breadth first search. There could be 3 trees, right, starting at, given this coin amount, right, 1, 2, 5, and 11, right, there'd be 3 trees, right, starting at these denominations. Then we'd have something like this, right, where each, it would be an n-ary tree, right, where the number of childs a node has depend on number of coins. So you take 1 again, right, but technically this size would be, the amount you would be at would be 2, and you could take 2 here, the amount you'd be at would be 3. You could take 3, you could take 5 here, the amount you would be at would actually be 6. Same would be with 2, same with 5. So if that's the case, then I think we know that the breadth first search, right, basically what we're searching for is the shortest path, but basically the length of the shortest path. That's the case, we know that breadth first search is the best candidate for this, since in the breadth first search we always expand on the nodes that are closest to us first, which tends well to basically giving us the shortest path. The problem being if we start at our root point, right, which is 1, and search for the shortest path, right, there's pretty much a lot of paths we can search. But if we start at 11, right, and search to get to, if we start at 11, right, and search for the shortest path to 0, right, we can actually get there pretty quick. So this is one of those cases like Thomas mentions, right? Is it faster to search from target or source, right? And in this case, right, we see that if we search from 1, 2, and 5, we have to search an inordinate amount of children. But if we search from 11, right, there's only so many paths, right, that get us to 11. since BFS lends itself to the shortest path, we know that if we BFS from 11 to 0, that we should be able to get to our, you should be able to find the shortest path pretty quickly. So I think we could implement this, right? If we say that our Q would start with the root, or with our target, which is 11, and we want to get to 0, right? The BFS, or the nodes that we can search that are close to us, are always going to be our current amount minus 1, 2, or 5. And whenever our current amount equals 0, right, then we'll know that that's the shortest path. Otherwise, if we never get there, we can return we'll return, if we can never get there, we have to return -1, right? We already handled the case where amount is 0. That's the case. Then we can just implement this BFS. Think through it just in case. Right, and in our BFS, we'll have an exit case if we can actually find the value that we're looking for, which is 0, right? Because we're going from top to bottom. Then we'll just return the length of that path. Otherwise, we'll be returning, if we never exit through there, then we're going to exit through the function. What I mean by that is, I have BFS, right? It's going to be a while loop, right? Exit if cur equals 0, return path length. And we can do this because we know there'll be a shortest path just as a property of BFS. Otherwise, right, we don't exit, so we likely want to return -1 because we never made it out. We never found a path at all. We didn't find any path. So that handles our two cases here. So to start, I think the best angle might be a Q. We went to BFS. It'll be a queue of tuples. Right, where the first value will be the node, right, and the path length, which will start at 1. Right, and what we'll do, right, this is how we'll keep track of the path length. So we'll say while q.length is not empty. Then we want to implement this, right? And we'll say const cur equals q.shift. This is actually going to give us a bit worse time complexity since we don't have a native implementation of a deck. This is a comment that Shubham recently mentioned, right? We don't have a native implementation of a deck, which means that whenever we take an element off the front of the queue, it's going to be linear time because we have to shift the elements down. We add an element to the end, it's going to be constant time. But even if you switch these operations, for example, if I added elements from to the front, right, with unshift, right, and took elements off the back with pop, we'd still have the same problem. So maybe we should learn to implement a deck on the spot. But for now, we'll just do q.shift, take an element off the front. Right, we'll say if cur. Oh, it's a queue of tuples, right? So we'll say cur, which would be our current node, right? And then length, which would be our current length we took to get to this node, right? Or the number of nodes we had, the number of vertices we had to travel between to get to this point. So if cur equals 0, we want to return length, which will automatically be the shortest path. Otherwise, we want to look over all of our coins. Say for const coin of coins, right? We'll say q dot push, right, cur plus coin, right, with length plus 1, because our length is going to get longer. to get 11, right, we should do, oh no, we're going to do cur minus coin since we're going top down. So do 11, our next 3 paths will be, right, 11 minus 1, which is 10, 11 minus 2, which is 9, 11 minus 5, which gives us 6. Then from there, we'll do the same thing. And I think this should work. Oh, I guess if we're adding 1, right, so we don't have to start our root at 1. Exceeded. Right. This is what I was worried about. This case. Oh, we actually have to stop past it. Right. So we don't want to search anything past the point. That's also something I neglected to look at, right? So what I mean by that is we're searching for 3, but we're at like 500 and we're still going. Basically, we want to prune the tree, right? If we can only add 2, right? Once we do 2 plus 2, we're at 4. We can't possibly get to 3 because we're past it. So we want to say if cur minus coin is greater than so we're going the opposite way. So if cur minus coin is less than amount. So if we're at 2, we're starting at 3, right? So if we do 3 minus 1, we're at 1. If we do 1 minus 2, we're at -1, right? So if cur minus coin is less than 0, I will say if cur minus coin is greater than 0, it's either way. Cur minus coin is less than 0, we'll just say continue. And then we'll change our input to there's so many. Wait. I think I remember this. There's 2 places you can check if cur equals. Wait a second. The issue that's happening here is that the value we're starting at with the coin is 1, right? And that's also our target amount. But since we check cur is equal to 0, we should also check no. Cur equals amount. For some reason my intuition tells me this is not. The way to go. I'll try it, but I don't think this is the right way to go. Yeah, that seems nutty. I'm realizing it. Oh my, no. I actually put in 11 instead of amount. Oh man. This is not as simple as I thought. I thought if we just went for the shortest path. I guess if we can go for the shortest path and also ignore what we've seen before. Right, because it's possible with 100, right? Even 100, 1, 2, and 5 that we're duplicating. A lot of work, even with the shortest. Yeah, even with the even searching from top down, we're still seeing a lot of numbers over and over again. So we'll say if scene has cur, then we'll say scene dot. If scene has cur, right? Then we'll just continue. Then we'll do scene dot add cur if we haven't seen it. That way, when we add all these extra values, right? If it would be a waste of time to check it, or we can push on a value we've seen already, we'll still skip it. Let's see. Yeah, this one's very slow. 925 is crazy. Yeah, why is this so slow? I think for the top down. So I feel like it should be faster, but it's very slow. How fast were the other ones? It's getting like 300, 290. So why is this one so slow? Might just be the nature of solving it with the VFS. Might just be slow. We skip values we've seen before, and we're also we skip values we've seen before, and we're also stopping us looking at subtrees that couldn't possibly get us where we're looking to go. Maybe that is the nature of solving this problem. Doesn't quite make sense because I got 373 before. Said the goal time was S10. BFS-based solution is the cheat code. The way we solved this one before is by caching our solutions. Doesn't quite make sense. I think we were able to get 400 milliseconds. We were able to get 500 milliseconds by actually visiting the entire tree. For some reason, even though we should be visiting less of the tree, it's still taking forever. Seen Haskell continue. Maybe we can speed it up just a little bit. We do else if cur minus coin equals 0. How much faster is this one? It's the same speed. We start at 11. We'll visit 10, 9, and 6. Is it what I did before? If we did coins, sort A comma B, B minus A to sort them in descending order. This is slightly faster, but this is still crazy. This solution I would also use on something like snakes and ladders, so I'm actually kind of curious. Why is this so slow? I don't understand why searching from 11 searching from 11 is slower than caching the shortest paths from every caching the shortest path from every point in the tree. In the other version, we visit every subtree, every unique node once. Then we can build the shortest path quicker between nodes, since we've already calculated the shortest paths from the node to the target node. Yeah, this is strange. I don't understand why this one's faster. This is just dynamic programming. I guess this is a simple Python BFS S times N with memoization. I guess I'm not seeing why we need memoization if we're doing a BFS. You said this is S times N. Well, at least presumably searching from the target, right? Let's just confirm one thing. Searching from the target has to be faster, right? What if we start from the way we initialize the queue would definitely change. Right, it would. We do queue dot push, right? We start with a coin, right, and a length of 0. And then we do cur minus. We actually do cur plus coin is greater than amount. It's just like marginally faster. Yeah, I think it's just strange that the BFS solution, I think I'm not intuiting exactly the mechanism by which we're producing work in the BFS, because we have a version where you almost visit the entire tree and cache the optimal subproblems. Somehow this version use a lot of space recursively, the DFS is much faster. That is interesting. That is interesting.